Okay, so this will be Algebra 2, Section 9.5 notes. The section deals with base E and natural logarithms. And if you remember, the whole chapter's kind of been about exponential functions, logarithms. So this is kind of like a special case here. We said a couple, I don't remember what video, but recently, when you just press the log button on your calculator, so if you just go on the calculator and press log of 100 or something like that, and try this out if you have a calculator, type log of 100, it's going to tell you that the answer equals 2. And what that should kind of tell you about the base is that, again, it's assuming that the base is 10, and the log of 100 then equals 2 because 10 to the second power equals 100. Okay, so 10 is the common base, and that's what's assumed on your calculator. We're going to see in this section and in the next couple that there's a different base. It's actually a number E that we'll talk about, and it deals with natural logs. Okay, so or it's called the natural log, the natural base. So let's look at an example. First off, we'll kind of do an application, and then we'll get into where this E comes from. Okay, so first off, this is an application of just exponentials, and it's something that I think it's a good example because you can kind of visualize this. This would be like if you put some money in a bank account and you're growing interest. Okay, you're actually growing what's called compound interest, and what's happening is you're getting interest, but then the next time they go to calculate your interest, you've already gained some interest. So it's kind of like you're getting interest on top of interest. So it's not just like a one-time interest thing. It's compounding. The interest is getting calculated over and over and over. Okay, and if you can see, this kind of follows the basic formula for an exponential. Was the general one was y equals sum a times sum b to the x power from back in the first section, I think. So it's just basically like, you know, there's your a value, which is your starting amount, which we'll talk about. Inside here, this whole thing is the b value, which is the growth or decay factor. And then the exponent is just n times t. So let's talk about what all these things mean. But again, have a basic understanding of the general formula in red there. It's always some initial value times some growth factor to the x power. Okay, so in this problem, again, that p is the initial value. When you're talking about money in a bank account, that stands for principal. Okay, it's just, again, it's your starting amount. These problems will usually say, you know, you invest $1,000 and blah blah blah. Okay, so that 1,000 would be your starting amount. Okay, in the equation you also see in the b part in parentheses there's r. Okay, so r is going to be the interest rate. You're going to have to know what type of rate you're given. It must be expressed as a decimal. Okay, so sometimes if they say the rate is like 6%, for example, you're going to have to convert that into 0.06 to use in this formula. Okay, so basically move the decimal kind of thing. N, the next variable in there, n is going to be the number of times compounded. The number of times interest is compounded or calculated. Per year, let's say. Okay. Okay, so that would be, for instance, if they say interest is compounded monthly. Okay, so a specific example, if monthly, and so in the problem they're going to say interest is compounded monthly or daily or weekly or whatever. So if it was compounded monthly, for example, in 1 year that would happen 12 times. So you would be collecting interest 12 times. Okay, if it's daily, you're getting interest every day, so you're getting interest 365 days in the year. Okay, and then finally the last variable deals with that also. We were saying it was per year, so the t value is going to be the number of years. How long are you investing? Okay, so how long is the money going to be in this account, basically? So let's do an example, put some numbers in here, and see what we got. Okay, so let's say you invest $1,300 into an account earning 4.5% interest compounded monthly, and you want to know part A, how much would you have after 15 years? Okay, so again, we know our formula. Y is going to be the ending amount. It's always going to be the principal times 1 plus r over n to the nt. Okay, and I guess instead of calling it y, we had called it a here. Okay, and the a kind of just stands for the amount, the ending amount. Okay. Okay, so in the formula, again, our principal, we started out with 1300. Okay, the 1 is just built into the formula, and what it does is it makes sure that the thing you're multiplying by is a number bigger than 1. So that makes sure that your number grows. So that's why it's 1 plus this rate. Okay, so you're getting 0.045. And since it's happening every month, that's happening 12 times in a year. So each time you're getting the 0.045 divided by 12. And then again, n in the parenthesis here, and the exponent I mean is 12. And we are doing this for 15 years. Okay, so 12 times a year for 15 years. 12 times 15 will get you your exponent there. Okay, so now it is just kind of a straight calculator problem. I would be a little careful. You know, it's definitely doable on one step. I would probably encourage you to maybe do at least a couple steps. Let's figure out what that number is first. Okay, so on the calculator we'll do our 1 plus 0.045 over 12. Okay, and again, it's definitely possible to do the whole thing in one step, but I personally like to break it down. So let's say that's our b value, that's the growth. Now if you remember in the formula, that is getting raised to a power. Okay, so 1.00375 is this number. Okay, I can't just multiply by the 1300 yet because the number we just found is getting raised to a power. So why don't we take that to the 12 times 15. Okay, so I'm just going to use my caret key, answer. The exponent needs to go in parentheses. It's 12 times 15. Okay, so this is that 1.00375 to the whatever 12 times 15 is. Okay, so that's 1.961555. Now that number needs to get times by the 1300 that we originally started with. It was 1300, yes. Okay, so if we do that, that should give us our final answer. That's how much your money will have grown. You'll now have $2,550.02. Okay, so again, we did this exponent part on the calculator already, and then that gave us a final answer of 2550.02. Okay, so not bad. We only started with 1300. We almost doubled our money. It took 15 years, so I guess it's a little bit slow, but hey, free money sitting in a bank account. You do a retirement account or something. It's going to be in there for a long time. Okay, so part B. Okay, how long would it take to have $2,700? So let's go back to the beginning. We have the 1300. You're putting that in an account. You want to know how long it's going to take until that reaches 2,700. So again, if you think about the equation, let's just rewrite it here. A equals 1300. 1 plus 0.045 over 12. Now here we know n, but we don't know t. I don't know that it's 15 years. That's where the variable is. And the $2,700 is the ending amount. Okay, so we have ourselves a little equation to solve. And we want to solve for something that's in an exponent. Okay, that's where logarithms will come into play in a second. Okay, so let's do a couple things. Let's simplify a little bit. First off, I would actually divide both sides by the 1300. Okay, so let's take that 2700, divide by the 1300, and that's going to end up being 2.0769. I'm just going to carry about 4 decimal places. So again, that was just dividing the 1300 out on both sides. Okay. And let's do a little more simplifying. We did this in the previous problem. That was the 1.00375. And now it's to the 12t power. Okay, so we have that equation there. Now is here. We got everything taken care of except our variable is still in the exponent. But we got rid of everything that was not part of the base. Okay, that 1.00375 is the base. That's the thing raised to a power. So what we need to be thinking here now is, since your variable is part of an exponent, that's where logarithms help us. Let's change this to log form and see if we can finish it out that way. So if we convert this into log form, Okay, the log, remember it's log, here's my base, so that gets written as a little subscript, okay, of the number over here has to equal whatever the exponent was, and it was 12t. Okay, that's my logarithm equation. Now the left side of this equation over here, this is going to be done on a calculator. Okay, remember we had the change of base formula that said from the previous video that if you have the log of some base, I don't remember what variables we used, but let's just say it was that, you can always just do the log of A on a calculator divided by the log of B. Okay, that's the change of base formula. So for this problem, it can be the log of the 2.0769. Okay, and again, that'll be in parentheses, and close that parenthesis up because you're dividing it by another logarithm. Okay, still equals 12t. Okay, so this left problem here can be done on a calculator. And enter it just like that. We're going to do log. It's going to open a parenthesis. We're going to put the 2.0769. Make sure you close the parenthesis, then divide by log 1.00375. Okay, and the left side of your equation should be 195.26558. Okay, so that still equals 12t. And now simply to get t, we will just divide both sides by 12. And that'll give us an answer of about 16.27. Okay, and again, t is measured in years. That's the number of years it would take to get to the $2,700. Okay, and that should kind of make sense. It should flow from what we did in part A. We said in 15 years we'd have $2,500. So part B was just how long would it take you to get $2,700. So we were almost there at 15 years. So that seems reasonable that it would take, about 16.27 years to do that. Okay, so again, that's from the beginning, not from after 15 years already. This is from like when you just first put the money in. It's 16.27 years. Okay. All right. So let's say consider investing $1 at 100% interest for 1 year. I'm just kind of making up some hypotheticals here. Okay, and let's say that the interest is compounded continuously. Okay, this is different. This is not monthly or daily. This is going to be like constantly. Okay, so let's see how that changes things. So the same kind of formula. Okay, the yellow, you can see that was what we were calling P before. That's the principal. 1 plus R over N to the NT. Okay, and again, we were saying the rate was 100%, so that's why R is 1. Okay, and what I'm asking is, if we do this continuously, okay, what N value should we use here? So let's think about this. Let me do a little simplifying in here first. This is a 1 on the outside. 1 plus 1 over N to the N power. Okay, just doing a little simplifying out here. And then technically we would not need to write this 1 out here if you multiply by 1. Okay, so my question is, what happens to that expression as the N value gets really big? Okay, so if I just keep putting bigger and bigger numbers in here, what would this thing equal, I guess, is my question. Okay, so let's think about that. Let's go to the to a table and let's see what happens. Okay, so if I choose different N values, so I'm just kind of picking these values just to see what happens as N gets bigger. This is that expression we just had on the other page. If we want to go to a calculator and see what happens, let's do that, okay? Because this is leading us towards something. So I'm going to actually do it in the table here. I'm going to do it as 1 plus, I'm going to use x so that I can use a table. So 1 plus 1 over x to the x power. So those x's are like where the n's were. And I just want to see what happens to the answer as I put bigger and bigger numbers in for x. Okay, so if I go to the table, we can see if I just use 1, the answer would be 2. If I use 2, there's the answer, and so on. So let's fill some of these in. Um, and again, just to kind of see it for the first one, again, we're saying that I'm putting in a 1 for that n. And I'm just seeing what this thing equals. So this is just 1 plus 1. It's just 2 to the first. It's just 2. Okay, but when we go to the second piece, if n were 2 now, to the second, so that would be more like 1 plus 1/2, so 1.5. 1.5 squared, I believe, was 2.25. Okay, is that what the table told us here? Yeah, 2.25. Okay, and again, this is just kind of leading us towards something. This process isn't something you'll have to like do in a problem or anything, but it's getting us somewhere. Okay, so think about what's happening to these values as the x's get really big. And let's go even farther. Let me change my table set. Instead of going by ones, let's go by 50s or something. And let's just see. So I want to get some real big numbers. Okay, so I'm going by 50s. Oh, some sort of error message here. Where's my table? All right, so there we go. So if you look at what the y values are doing, they're around this 2.71 number. And they're getting a little bigger and a little bigger, but they're not growing real fast at all. I'm out to 700x, and the y is still right around there. Okay, so that number that they're getting close to, okay, let's see where, that number that they're approaching, okay, if we kept going, they were getting close to this 2.71, da 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 da. Okay, that number is actually this number that we're going to name e. Okay, and it has a lot of uses in calculus and in sciences and just natural uses. That's why it's called the natural logarithm, so, or the natural log base. So it's 2.71, I believe 2.718 something or other. Your calculator actually does have a button for it if we wanted to check that out. Second quick, so we're going to use it a little bit. It's actually right below the pi key. You got second, e, second the division symbol, and you can see that's technically what it equals. Okay, or what we also might do is e to a power. There's a button over here, second e to a power, if we needed e to the third power or something like that. Okay, so more on that in a second. So that number again, that's e. It's an irrational number. It's like pi. You know, the decimal goes on forever and ever, no pattern. That's what it is. And what ends up happening is, if we're doing a compound interest problems like the ones we had just done, it's kind of like, what would the case be if n were infinity? Okay, if it's continuous, they're giving you interest just constantly. It's not monthly, it's not daily, it's not every second even, it's just constantly. In that case, we use this formula, and it's the same. Everything else is the same. This p is still your principal. E is the new number that we just talked about. So this e basically replaced the 1 plus r over n. Okay, r and t are the same as they were before. Okay, so let's look at a quick problem with using that. And the way you're going to know it's one of these problems is that it's compounded continuously. Okay, so if you invest $3,700 into an account earning 5.25% compounded continuously, how much will you have after 10 years? Okay, so that's the only difference here. When you see that word, you know that it's the one that uses the E. Okay, so it's like E equals PERT, right? Shampoo, PERT plus. Okay, if it's continuous, P times E to the RT. Okay, so this part A should be very similar to what we did before. The amount is going to equal the principal times E to the R times T power. And just make sure the R is a decimal again, so the 5.25% decimal needs to slide over. It's going to be 0.0525 times T, what do we say, how many years? 10 years. Okay. So that one, pretty much a straight calculator problem. 3,700. Okay. 3,700 times E to the 0.00, or no, I'm sorry, it's just 0.0525 times 10 power. Hi. And that should give us our answer right there. Okay, so that would be our answer, $6,254. $6,254. would be our amount after the 10 years. Okay, and what was the cents on that? Oops, wrong one. Round that up to 70 cents. Okay. Okay, so part B then, similar to what we did in part B in the other problem, how long will it take? Let's say we want to triple our initial investment. Um, so we started with $3,700, so that's our initial amount, but the ending amount would need to be triple that. So times 3 would be $11,100. So we'll set that in as our A value. The rest of this will be the same principal, same base, same rate. Okay, it's just that we don't know how many years. So how long is it going to take? There's our variable t. Okay, so this is another problem where the thing we need, the variable, is part of the exponent. So it's going to use logs eventually, but we first want to get the exponent by itself. So I'm going to divide by the 3,700 first. Okay, and this shouldn't be a surprise. The left side's going to equal 3. Right, it's 3 times what we started with. So 3 is going to equal e to the 0.0525t. Okay, and now we need to know how to finish this. So just like before, once we get to this step, we can change to log form. Okay, so if we change to log form, in this case the base is e again, and this is new, I guess. The base is e, so log base e of 3 is going to equal the exponent. Okay, so here's the new part. Okay, we are usually using a number like 10 is the base or something. If the base is e, okay, there's a button on your calculator that uses a base e, and that's the natural log. Okay, so log base e is the natural log. There's an ln button. It's right below the regular log button. Okay, and it just means it's the natural base, and e is the natural base. So there's a shortcut. You can just switch that log base e just to ln of 3. Again, your calculator will know what that is. This side we haven't messed with yet. And then to solve for t, I would just divide both sides by that 0.0525 and let our calculator handle this. Okay, so that's going to be t equals, and let's do this on the calculator here, the ln of 3 divided by 0.0525, and that'll give us our answer. Okay, so again, natural log's over by the 4 here, ln of 3. Make sure you close up that parenthesis. That's the only thing we're taking the log of. That log is getting divided by 0.0525. Okay, that cannot be part of the log, so we close the parenthesis. And there's our answer. It'll take around 20.9 years to triple your money if you're earning the 5.25%. Okay, and then one more quick example solving a problem with e in it. So this is just kind of an equation they'll give you. It's not a word problem that you need to set up. But let's go ahead and solve that real quick. Again, you're noticing where your variable is in the exponent. So let's get that by itself. Let's do what we can. We'll subtract the 4 first, and we'll have 3e to the negative 2x equals 6. And then again, I want to get the base and exponent by itself, so that 3 out there needs to be divided out. So we'll divide both sides and get e to the negative 2x equals 2. Okay, so now the exponentials by itself, we're ready to change to log form. Okay, so if we just convert this into log form again, log, the base is e here. Okay, we're taking the log of 2, and it's going to equal whatever the exponent is. Okay, so we got log base e of 2 equals negative 2x. Okay, the new thing we just mentioned, if the base is e, then it's a natural log. So we're going to use the natural log of 2 equals negative 2x. And to solve that for x, we will just divide both sides by negative 2. Okay, and again, don't forget, you're not dividing the 2 by negative 2. We're dividing the natural log of 2 by negative 2. So that's going to be just a calculator problem, parentheses around the 2 in the numerator there. and we'll get a final answer. If we do natural log of 2, gotta close this parentheses. I know I'm saying it a lot, but it happens all the time when we forget. And we divide by -2, and that should be our answer, -0.35 if we round that. Okay, so that is an example. Here are a couple practice problems to look at for homework for this section. And we will continue in the next section with some more word problems, everybody's favorite. All right.